Okay, last week we did simple linear regression. Simple linear, we call it bivariate, simple linear regression. That means one predictor. Now we're going to add more than one predictor. So it's called multiple linear regression. So that's what we're going to do today, multiple. So what do you mean multiple? That means multiple predictors, right? Multiple predictors or multiple independent variables and one dependent variable. So last week I asked whether BP depends on BMI. Now I can ask whether BP depends on BMI, depends on age, depends on cholesterol, so more variables. So look at the equation. Last time for simple linear regression, only until x1, one predictor. Now we're expanding to more than one. So basically what you want to know, whether y depends on x1, whether y depends on x2, and so on. So the b1 is a slope for y versus x1. b2 is a slope y and x2. So the b1s to bp, they are the regression coefficients. Actually, the slopes. So last week, we talked about slopes, right? Slopes, whether they are flat or inclined. So how do you know the slope is 0 or not? We look at the p-value for each of the predictor. So when the b1 is 0, 0 times whatever x1, this will be 0. And the b2 is not 0, this time this won't be 0. So actually what I'm looking for is whether b1, b2, and so on, are they 0 or non-zero? 0 means slope is flat, so y does not depend on x1. How do you know that? For each one of the coefficients here, there will be a p-value. For x1, what's a p-value? If the x1, the p-value less than 0.05, we say y depends on x1. If supposing the p-value for x2 is more than 0.05, then it say y does not depend on x2. Okay, later we'll see some examples. Right. So this context now, let's say 3 variables, x1, x2, and x3. So actually what I'm looking for, the b1, b2, b3, are they 0 or non-zero? So for number 1 here, this slope is not 0. The base slope is more than 0. This is flat, there's no slope, so b2 almost 0. This one here, even though negative, in absolute value, still more than 0. So that's the situation. We say, yes, y depends on x1. This situation will say, y does not depend on x2. This one will say, y depends on x3. So since it's positive, the higher the x1, the higher the y. Here's negative, coming down. The higher the x1, x3, the lower the y. So these are patterns you're going to look for in a multivariate. It could be positive, it could be negative, it can be 0, right? All this based on some p-values, you obtain this whether each one, whether significant or not. All right, assumptions. We have seen this assumption earlier for simple linear regression. The residuals. We have seen what's residual, difference between observed and predicted. Smaller the residuals, the better the model fit. So residual terms must be independent, right? How do you confirm this? From the plot, residual plot, they must be random and must be distributed normal. We save the residuals and check that. So now you would add one more additional assumption. the axis must be independent. Axis here meaning the predictor variables must be independent of each other. That's why it's called independent, right? Which means they should not be highly correlated. Independent means they should not be highly correlated. If they're highly correlated, then we have a problem of multicollinearity. So in simple linear regression, we check this, whether model fit, is it okay, not okay. Now, in addition to this, you got to check this as well. Okay, don't bother, just one click button, a value for multicollinearity index will come. Based on that, we interpret. So remember, you're going to have additional. Of course, regression has a lot of assumptions, but these are the basic assumptions you must test. Simple linear regression, only this. Multiple linear regression, we add one more assumption here. Right. So what is multicollinearity? MC is a correlation between two independent variables, right, in the regression model. Okay. MC can be assessed by that's called variance inflation factor. Later, when you do an analysis, we look for this value. I don't want to go details how to interpret. The VRF less than 5, no serious problem. VRF 5 to 10, there is some problem. VRF more than 10, serious problem. So VRF problem more than 10 means what? At least two variables are very highly correlated. So later we'll see an example, okay? So multicollinearity for any multiple analysis, multivariate analysis, we have to check this. So what does it mean? That two variables are highly correlated. Example, let's say, husbands and wives' level of education. Husbands and wives' level. It could be highly correlated. Supposing they found each other at the university, right? Supposing they were classmates, classmates. That's a possibility, the high correlation. That means higher the level of education for husband, most likely higher the level of education for the wife. That can be very high correlation. So that must be detected and something must be done. So remember, these are the cut points. Okay, example. So association between age, weight, BSA is body surface area, body surface area, height. So these are the independent variables, and BP. That's a dependent variable. Again, 3 steps. We're going to scatter plot, correlation, then regression. Same as your simple linear regression. All right. So in scatter plot, you're going to ask for metrics. Okay, metrics. Otherwise, there'll be only one box here, one variable can go in, one variable, right? So multiple variables can go in here. Right? Remember, there are more than one box. If a bivariate, y-axis, x-axis. So now you're checking all these, how are they connected to each other? Remember, they should not be highly correlated. If they are, there is a problem of multicollinearity. Right. So we do exactly same. Put the variables and click OK. Okay, look at the output. So it's a matrix plot. We don't have to see one half, right? Just one half is enough because that's a mirror image. This and that, the mirror images. So let's say we see only one half. Block this part. So look at the last row. The vertical axis BP, SBP, this age, weight, BSA, and waist. So this particular scatter is for age versus BP. So you can see older the person, higher the BP. Looks like there is a positive association. Same as height. Heavier the person, higher the BP. Body surface area, bigger the body surface area, higher the BP. Waist, bigger the waist, higher the body surface area. This looks very tight, right? This is not so much a bit loose. Now on this side, beyond this red box here, this side, this is a connection between the independent variables. For example, this is weight and age. This is body surface area and age. This one is waist and age. Now look at this one particularly. Body surface area and weight. Generally, people are fat. The body surface area is very much higher, right? People are fat. The body surface area increases. So heavier the person, higher the BSA. So this kind of thing, we can expect a problem of multicollinearity because the pattern is very strong. They're highly correlated with each other. So we suspect, based on the figure itself, we can suspect there could be a multicollinearity problem. So first step is scatter. Second step, correlate. Again, we do exactly what we did last week. Last week, we need two variables. Now you have more than two variables. Bring all the variables inside here and click OK. The results. Again, on the right hand side, above the one, this is a mirror image of what is here. So let's block one side. Okay, let's say on this half, again BP. BP versus, you look up here, BP versus age. Next one, BP versus weight, body surface area, and waist, right? So BP versus age. This P value, so this R value, that's a value which is very significant, P value. And also it's more than 0.3. So that is an association between this and this, right? That means what? As higher the older the person, higher the BP. Next one is weight, right? 0.2, that's a weight. Again, similarly, significant P value, so that's a P value less than 0.001. Next one is body surface area, same thing. And last one is waist, same thing here. Again, is there a problem multicollinearity? Look at this part here, this between BSA and weight. This between BSA and weight. This one here. If we see any pairwise correlation more than 0.9, they're bound to be multicollinearity. So this value here is more than 0.9, 0.96 something, okay? Therefore, is it too high? For all practical purposes, yes. So we saw in this particular figure, they're very highly connected to each other. There is a possibility, we don't know yet. Correlation between weight and BS is very high. So we can expect a problem of multicollinearity, right? So we'll confirm later. So what's the problem multicollinearity? You can see that heavier the person, BSA is high, very much linear pattern. We want it to be something like this, not so much the R value should be right, like in this range. So it's called pairwise correlation. meaning taking only two variables at a time. Pair, pairwise correlation. So done, scatter, correlate. Next, go to regression. Same like last week, BP goes here. Last week, only one variable independent. Now you put all the variables in the independent. So now we have multiple linear regression. Multiple linear regression. Time being, just click OK and look at the results. Follow the sequence. What's number one? Number one, in our table, P less than 0.0001 plus less than 0.05. So interpretation is SBP depends on at least one of the four. Don't say BP depends on all. BP depends on at least one of the four. What's the next question? Geeta?
Which one?
Okay, again.
Which one?
Which one? BP depends on at least one of the four. So what's the question? Ask again.
Which one?
Which one? Now I come to coefficients table. In the coefficient table, look at the last column. So these are p-values. So here, p-value for age, weight, and weight are significant, not BSA. So this p-value for ANOVA table less than 0.05. Therefore, BP depends on at least one of the four. Which one or which ones? We go to the coefficient table and read from here. BP depends on age, weight, and weight only. Then you write the equation, step number 3. Even though it's not significant, we still write the equation. So constant, 48, age, 0.684, weight, 0.596, BSA, 0.388, and waste, 9.749. Same like your simple linear regression. And our table, does it depend? Yes, at least one. Which ones? Write it down. And write the equation as it is. Don't drop BSA, right? As it is, because it is the model. Then how to interpret this? Last time only until here, only one variable. We say every unit increase in BMI, BP expected to increase by 2 points. But now there are other variables as well. So you shouldn't say every unit increase in age, BP expected by increase by 6848. But what about other variables? So correctly you must say every unit increase in age, BP expected to increase by 0.6848 units, provided other variables remain unchanged. When you're comparing age and BP, using this particular coefficient, you must control for other variables. Other variables remain unchanged. Same thing, when you're comparing weight, for every unit increase in weight, BP expected to increase by 0.596 units, provided other variables remain unchanged. Right? Again, in the equation, these are the beta ones, B1, B2, B3, and B4. So you wanted to know whether the number 1, the number 2, is the number 3. Basically, slope is not 0 or negatively, right? So when it comes like that, we say y does not depend on this value. How do you know this? This p-value. Take the p-value for this. If it is flat like that, this p-value will be more than 0.05. Becomes like that, this value, slope is not 0, then p-value will be less than 0.05. In our example now, for all the other variables, p-value less than 0.05. Therefore, age, the slope for age, weight, and BSA are not 0. For age, weight, and waist are not 0. For BSA, the p-value more than 0.05. So we say BP does not depend on BSA. So writing equation, we use unstandardized beta coefficient. Unstandardized. Then there is standardized coefficient. So what's the use of this? This is look for relative importance. Among these values, which is most important? We can't say, oh, this is 9.7, this is most important. They must be standardized. Right? We get this value. Now you can compare this. Among the variables, the most important is age, followed by weight, then waist, and the last BSA. Right? You can compare 0.4, 0.2. I can say age is twice as important as waist because they're standardized. I can't say that same thing based on this because they're unstandardized. Why? Age is measured in age, weight is measured in kilogram, BSA is measured in centimeter square, waist is measured in centimeter, different measurements. But here all are standardized. So this is for writing the equation. This is for identifying the relative importance. Here we can say age is 2 times as important. More or less is 2. We can say waist is 2 times as important as BSA. Right? So that is next. We done 4, 5. Okay, now come to R square. So that's R square value, 636. So what does it mean? 63.6% of the variation in BP, is explained by the 4 predictors. Don't say explained by age, weight, and waist. Because in this model, there are 4 variables. Waist is there, BSA, age, weight, all the 4 variables are there. So here, depends on at least one. Which one? Write the equation, explain it, R square. There are 4 variables. So we say that much explained by the 4 variables. Any questions?
Yes, Professor.
Yeah.
Regarding the standardized coefficients,
yeah,
the beta, because all these 4 variables add up is 1. So that means it's 100%, right? So if that's why it's important, we have to identify which one is MC. Am I right?
MCA not yet. MCA not yet. What mean MCA?
The multi-collinear
Not yet. The one not yet. Not yet.
So, but this is very important to see the importance among the variable.
Yes.
So so that is that's why important for us later to learn how to identify, right?
So what does it mean here? The most important is age.
Right.
Can you change age? Can you modify age?
No.
No. What's next important? Next important?
Weight.
Weight. Can you modify weight?
Can.
Can. What's next?
Waist.
Weight. Can you modify waist?
Can.
Can. BSA is not significant, right? So some of
Yes.
the variables are modifiable, some are not, right? Some are
Yes.
modifiable. So in terms of this, in terms of practice,
Uh-huh.
how is it useful, right?
Right.
Go and
Yes.
reduce the weight.
My question is for BSA,
Ah,
because it's a very similar to weight.
weight.
Yeah, so if BSA is little bit more, so actually their weight and BSA may be combined together is a similar things. For example, okay, so probably will be higher than age.
Right.
So that's why it's important for us when we learn to make sure we have to identify the any
Correct.
collinear.
Right.
Yes.
But right
Okay.
now,
Yeah.
weight and BSA, weight in kg, what
Okay.
is the first area in the meter square? Meter square.
Right.
Can you add these two?
I don't think so.
Cannot, they're different units.
Yes.
So prediction by the units, age,
Ah. Okay.
kilogram,
Yeah.
meter square, and waist measurement. But among these, which is most important, we say relative importance.
Age.
Supposing the last value here is 0.6, this
Okay.
value is 0.6. So which
Okay.
one will you modify first? Weight or waist? Supposing,
Then
okay, 0.7,
waste.
let's say 0.7. Is it
Then
twice
we
as much compared to this?
yes.
Yes. That means you go and do something with the waist first.
Okay.
This is for implementation. Where do we go first?
Okay. That's
This
very
is
good.
for writing a model for prediction.
Okay.
You okay?
Yes.
All right.
Thanks.
So that's the sequence. 1, 2, 3, 4, and 5. All right. Next, testing the assumptions. Remember the assumption? There should not be multicollinearity. So later we're going to do this procedure. 36. Check this and just click OK. We look at the last column. That's a VIF. What's the highest value here? Highest value.
Wait.
No, the highest value doesn't matter where. What's the highest value here? 8.5?
Yes.
Is it more than 5?
Yes.
Our criteria is now below 5, no problem. 5 to 10, some problem. More
Yes.
than 10, serious problem. So here you can see there is a problem of multicollinearity.
Right. Okay.
Right? So now
Yeah.
the assumptions here, they must be independent. How do you measure it? MC multicollinearity. What's the rule of thumb? Less than 5, no problem. 5 to 10, there is some problem there. Some authors only go for more than 10. Right? Below 10, they say okay. Right? But you'll be strict. That's why you follow. Next, the example we saw in the scatter plot between BSA and weight. They are closely knit. Most likely, he may have problem, but he can't confirm it. N correlation. So we found this 938, which is more than 0.9. So we suspect, yes, there could be a problem between BSA and weight. And you do regression, it's not complete yet. Now we are the BIF. The highest value, I normally don't bother about this. The highest value is 8.5, which is more than 5. Therefore, you confirm there is a problem. On scatter plot correlation, we saw some evidence. Now we confirm that's a problem. In that case, what do you do? In that case, what do you do?
You have to
You drop BSA between weight and BSA, which is easier to measure.
wait.
Easier, right? Imagine
Yes.
Imagine an elephant and a rat. Which is heavier? Elephant and cat, okay? Elephant and cat. Which is heavier? Which is heavier? Elephant and cat.
Cat.
They're heavy, more weight.
Heavy.
Elephant and cat. Which is heavier?
Elephant.
Huh? Fully grown elephant and fully grown cat.
Elephant.
Elephant. We cut elephant, take out the skin, cut the rat, take out the skin. Which one's a bigger area?
Elephant still.
Elephant. And that's
Yeah.
why these two are highly correlated. Which is easier to measure? Elephant's weight or elephant's body surface area?
Weight.
Weight. Sometimes by inspection, these two are very highly correlated. This is easier to measure than this. I drop this in the analysis. I redo without BSA. That means I go back to my analysis. I drop BSA from the analysis.
Professor,
Yeah.
can we choose according to the standardized coefficient, the weight?
Okay. So
Because the weight is so higher, better.
yes. So weight is a better, right? But if
Yes.
you drop weight, this may change, right?
Yeah.
We don't know.
Yes. Okay.
Sometimes you also decide which is easier to measure. After all, they're highly correlated. Like measuring one is like measuring the other.
Okay.
So I may decide, okay, let's drop BSA. So I do the analysis without BSA. A table will come without these values. That's one way. Secondly, you also can ask SPSS to help. I skip this first, SPSS to help. So all the variables are there. Change this default enter method, change to stepwise, right? Currently is enter. Look at this, enter. Where all the variables enter into the model. I pull down and change to stepwise. So I go and tell SPSS, take in one variable at a time according to the relative importance. Keep doing until what's left behind is not important anymore. Let's do the results. So this is called stepwise method. Stepwise meaning step by step. This is model one, refer to first step. Which variable entered first step? Which variable here?
Age.
Age came in first.
Yep.
Step two?
Weight.
Weight comes in. Step three?
Waste
What happened to BSA?
is the last one.
Did he come in? Did BSA come in? Yeah. It stops at
No.
3, right?
Yes.
It means when this variable is already in the model, BSA does not explain much.
Oh, okay.
So currently, what's R square? 636, right?
Yes.
So what about others? Carry on response. Currently R square 636. What variables? Weight, BSA, age, and weight. Now, you follow this scale. Model one refers to? Model one refers to?
0.68.
No, what's model one?
The model one is for all, for age.
The model one only for age, right?
Oh, I see. Okay.
Age R square is 46.5%.
Right.
Age alone explains 46.5%. Next, what's model two?
Age and weight.
Age and weight. Age and weight, model 2. So this is age alone, R square. This 0.142 is over and above age. How much weight contribute? Age already contributed 46%. Now we add weight. Explains further 14%. These two add together, is it this value? These
Yep.
two add together.
Yes.
Is it equals this?
Yes.
Come on, respond.
60.6.
These two add together, right?
Yeah.
7, 0, 6, right?
Yeah. 0.607.
Model 3. What comes in? Waste comes in. Model 3 waste. So this additional 0.3, that means 3% extra. 3% extra. Add up 0.636. So that's how it goes. Age alone, weight added, add up to 60%. Waste added goes up to 63.6%. This means that age alone explains 46%. Age and weight explains 64%. Age, weight, and weights explain 63.6%. Now, your R square just now enter method, all the 4 variables were 63.6, is that right?
Yeah.
All 4 variables. Now, with only the 3 variables, is it
Same.
almost the same?
Yes.
It won't be exactly the same. It's rounded up. They're almost the same.
Yeah.
So you want to carry 4 variables or 3 variables enough?
3.
3. Which is easier to measure, 4 variables or 3 variables? 3 variables, better to measure, easier to measure.
Yes.
3 variables, right? The R square, it's not much different. It's a good trade-off. Less number of variables, predictors, R square about the same. It's not exactly the same, about the same. Therefore, in this particular model now, what we had a problem of multicollinearity. Look at now. Model 1, age alone. Age and weight, highest value less than 5. There's no multicollinearity. Age, weight, and waste, that's highest value less than 5. So resolve the problem of multicollinearity. Now I can write the equation. Write the equation. Now don't go to this model and drop this value. No. You see the coefficient changes. So now from this, we write the equation. The last model. The stepwise age, weight comes in, waste comes in. Take the last model. That's model 1 until model 6. Take the last one. So now we write the equation. There will be slight changes, slight differences in the coefficients. So that's what you have. Right? So that part is for modeling. Right? Later we'll see how to do the write-up. Okay, before that, the assumption. Testing the assumptions. You did tested 1. What's the other assumption? What's the other assumption?
Independent.
The
Each variable.
Residuals must be independent. We done this. There was a problem. And we know that stepwise method eliminates this problem. But what about this? So now I'm going to test this again. We have done last week. Whether independent and normally distributed. Right. Testing assumption. We perform the analysis again. Select plots. See the plot. Recede always in the y-axis. Predict always in the x-axis. So plot this. We go to scatter plot. Same time, save the residuals. We done it last week. Save the residuals. So look at the plot. Is there a pattern or is it random?
Random.
Random. So what's not random? The plots going up and coming down. It's not random.
Line.
They're going up like that. Not random. Very broad and narrowing down. It's not random. So this pattern is random. Therefore, we can say residuals are independent. Normal. The test for normality, lesson 4. Lesson 2, sorry. Normality. Take p-value. Run the analysis. Sample size more than 50. So I use Komograph in the middle. The p-value is more than 0.05. Assume residuals are distributed normal. So the first analysis, and I did this analysis now here, we found that the model is not valid because the multicollinearity is very high. But the residuals are okay. But still not enough. You must find a way how to resolve the multicollinearity problem. We asked SPSS, can he help us? Right? Change the method to stepwise. I did very well. The R square does not differ from the original model. And your VIF problem is resolved. Questions?
Professor, I have a question again. So that means we have to continue to test the variable, the independent variable, until we can finalize the final equation, right?
Final equation. Look at the write-up, a simple write-up. This was the original equation, but we have the assumption multicollinearity not met, but the problem was there. Then we did the stepwise. That's the final equation. So you can see the slide changes here. When you drop 1, the coefficients will change. Not major, very minor, because BSA does not contribute much. But still, we must show the original model. The original model still has the BSA. And I'm telling there is a problem. Right? Don't go straight to stepwise. Show that there is a problem. So what he did, you try the stepwise. And that was resolved. Questions? So similar steps as in your simple linear regression. Scatter. It's a simple. We have matrix plot. Visualize. We can foresee some problem there. Correlation. Again, this value is very high. Right, let me ask you. This R value is 0.38. Like it 0.9, okay? Let's say 0.9. 0.9. What's 1 minus 0.9?
0.1.
What is 1 over 0.1?
It's a ratio, 1 to
Yeah,
9.
What's 1 over 0.1?
10.
11%. I mean,
I'm taking roughly 9.9. What's 1 minus 0.9?
1.
0.1. 1 divided by 0.1?
Oh, 1 divided by 0.1.
10. How much?
Yeah.
10.
10. That's a VIF, okay? Of course, must correct for the thing, roughly. If this is more than 0.9, pairwise, we can say there is a problem. But this 0. Let's say 0.8, we still don't know yet. But based on this correlation being more than 0.9, we can say outright there is a problem. So what's VIF actually? 1 minus R, 1 over 1 minus R. That's a VIF. So whenever I see more than 0.9, I know that's a problem.
Right.
Right? But 3.8 doesn't mean there's no problem. Yes, I still must assess multipolarity. So that's what I saw in the correlation. Then we went to regression. We did the 1, 2, 3, 4, 5. And then we test assumption, multipolarity, which failed. At the same time, we did this, residuals. Residuals are good. Now I try stepwise. 3 steps. R square, not much a difference. Supposing this 63%, this only 30%. That means losing so much of explained variation. That's not good. And finally, we have resolved this. Are there a lot of tables? The analysis, are there a lot of tables? Are there a lot
Quite a
of
bit.
Yes?
Quite a bit of stuff. Yeah.
What are you doing? Are you copy and paste all the tables? Look at somebody.
No.
Look at somebody. That's all we need. Don't copy and paste all the tables. You still happy with you want to have the table? Put appendix. See, I'm telling what I want to know. Association between age, ways, BSN ways was tested using multiple regression analysis. I'm telling what I did. The results are shown in table X. I'm telling these are results. And then I'm describing, interpreting what is in the table. Here, what I want to do, how I did, where the results are here. What did this statistics means? They're telling, as shown in table X, SBP associated with age, waist, and weight, right? Based on the p-values, 1, 2, and 3. The highest VIF is 8.51, which is more than 5. There is a problem of multicollinearity. With this, I write the equation. You don't have to explain every unit increase, you don't have to, but that's what it means. Then R square. R square was 0.36. What does it mean? 63.6% variation was explained by the 4 predictors, all 4 predictors. Right? In stepwise analysis, there are only age, weight, and waist are significant. And the R square value was 636, not much different from here. The residuals were independent and distributed normal. So that's the final equation. It's not here. That's my final equation. Right? So step by step, what have we done? Tell what you want to know. Tell how you did it. Tell where the results. And tell what the results mean. Are we clear?
Yep.
All right. Okay, let's do that. Open the data file. Which data is that? Blood pressure, right? Have you all got the data file? Blood pressure?
Yes.
All right.
I got it.
Now, how come other students are not conversing, are not participating in the class? I can't remember the names. Jeffrey.
Yes, Prof, I'm here.
You have any problems?
No, I'm following. Yeah, everything.
Okay. Gita,
Yes, Prof. I'm here.
can you follow?
Yes, can.
So I give exam now. Can you do it?
Can.
Why the can?
Try my best.
How do you give it step by step? Just do it.
Yeah, step by step I can do.
Can, right?
Yes.
That's all I want. All the information, all inside here. Okay, let's do it. Right? Normally, we don't do all this, but to visualize this, just visualize. Okay, data. Okay, that's my data. Right? All the variables, blood pressure. So open the file, blood pressure data, and do step by step. All right. So we start. Let's start visualizing this. So go to graphs, legacy dialog, scatter dot. You follow the information in the yellow box. Earlier was simple. Now go for matrix, more than 2 variables. So bring all the variables which are interested in. Age, weight, BSA, waist, and BP. That's all. Click OK. Okay, compile the figure. All right. All right, so this is a figure from your notes. Right. So you can see that. You can see that the last row, BP versus weight, right? Something is wrong here. It's not weight. Huh? Let's go to data and correct it. Go to data, editor, variable view. In variable view, this is a mistake. All right, it's age, not weight. Right. So I did my scatter plot. So you can see how, what kind of a pattern we have. BP and age looks linear, weight looks linear, surface areas look linear. This a bit, right, but still linear. But the problem is here. Body surface area and weight. So you can foresee a problem of multicollinearity. And we move on to correlation, strength of association. So for that, analyze, correlate, bivariate. Again, this pairwise. Bi means pair, right? Pairwise correlations. So bring the variables, age until BP. Okay. The last column, last row, we can see how these are correlated. Right? So this is BP versus age, weight, body surface area, and waist circumference. Pairwise, all are significant. Pairwise, all are significant. And notice this between weight and BSA. This value is very high. So you can foresee a problem. I mean, more or less can say there is a problem. Anything more than 0.9 we can say there is a problem. Okay, let's go to regression. All right. Objective. Test the association between BP dependent, or test if BP depends on age, weight, BSA, and waist. Going inside. Okay, let me do the multicollinearity as well, same time. Go to statistics. Click statistics. That's a co-linearity diagnosis. Co means together, linear means straight line. Co-linearity diagnostics. That's for testing VIF. Continue. For testing residuals, go to plots, same as what we did last week. Y-axis always residual, standardized resid. Z was standardized. And the x-axis is predicted. This is for checking whether the residuals are independent. Residual plot. Continue. Go to save button. Save. Check unstandardized. Continue. Is Aini in the class? Aini? Narayani? Narayani? Okay. Jeffrey.
Yes, Prof.
How many clicks?
A lot.
A lot.
1, 2, 3, 4, 5, 6, 7, 8.
Let's reset all of us. Reset. We're going to do one more time.
Okay.
All right. Jeffrey, what do you want to know?
Want to know the SPP and the
Whether he can depend on
age, weight, BSA, and waist.
weight, BSA, and waist, right? Independent. So this says that the BP depends on these variables. So going to the assumption testing as well, same time. The statistics ask for co-linearity diagnostics. In notes. Right, testing assumptions, this one. Jeffrey, how many clicks already? No, it's okay, no, right. Right, next. Plots, residual plot. Okay, I've shown in the notes. So do exactly. Y-axis, resid. X-axis, predict. Continue. Next, look at the note, save. Save the unstandardized. What is residual? Difference between observed and predicted. Continue. And click OK. That's all. You know, those days, how long would have taken to complete this, even without the calculator? Everything has to be done manually.
My gosh.
Right? We should do matrix transformation. And the matrix transformation, one goes wrong, finish. Okay. So whatever I need, the whole thing is there. Let's see the steps. Step 1, ANOVA. P less than 0.05. BP depends on at least one of the four. Which one? Look at the coefficient table. Under these correlations, all except for BSA. You can write the equation and check the collinearity. There is a problem. How much does it explain? 63.6%. Step 1, step 2, step 2. This is not significant. Write the equation. There is a problem. And how much does it explain? 63%, 0.6% explained by all the four variables. So don't say all except for BSA, okay? BSA in the model. Next, let's check the residuals. They are random. The VIF, we have seen just now, is more than 8. The assumption is not met. And we asked SPSS to save the residual just now. Let's test whether residuals were normal. Analyze, descriptive 36, explore. We've done this many times. Take the last variable. That's a residual 1. Depend on left. Plots. Ask for normality plot with test. Continue and click OK. Okay, so 350 sample size, Mogara Siminoff, p-value 0.181. So residual assumptions are okay. Residual assumptions are met. The only problem is multicollinearity. I'm going to ask SPSS whether it can give some help or not. In most cases, resolves this problem, right? In most, but not necessarily all cases. Let's do it. Analyze, regression, linear. Currently, the methods enter method. So pull down. A lot of methods here. Normally, the stepwise will do. All right. That's all. Now after that, sorry, one more. Go to R square. Going to see R square change. Look at this now. Check statistics again. 36. In statistics, check the box R square. R square change here. I want to see how the R square changes as the stepwise proceeds. Okay. 36. We already done this. Ask for R square change. Continue. So stepwise method now. Okay. Again, 3 steps. First step age. Second step weight. Last one's waste. BSA being excluded. And then the first model age alone explains 46%. Second model, age and weight 60%. Third model, age, weight, and waist circumference 63.6%. After that, it stops. So what is not in? But BSA not in.
Professor?
Yeah.
Is it automatically, because BSA is very insignificant, the system will automatically eliminate it?
No, it takes one by one. So age comes in first, right?
Yes.
It takes one by one. Age comes in first, all right? explain so much. Then weight comes in, explain additional 14%, which is significant. So adds on. The last one, your waste comes in, explains 3%, that is significant. So adds on to 607, become
Okay.
right. Now, supposing GSA,
Mhm.
GSA would have been very, very small, right?
Yes.
Very, very small. Not it won't be significant. That's why BSA was dropped. Are you okay?
Yeah.
That's
So
why,
the system will automatically will take the BSA out because it's
doesn't
not
explain.
it's
Doesn't
for slow.
explain much. It does not explain much.
Okay.
All right.
Thanks.
So you don't have to go through ANOVA again. Okay, ANOVA, whatever significance taken. So don't have to explain this. And the table now, this model 1, age, model 2, age and weight, model 3, age, weight, and weight in the base. We take the last one. Write the equation. Check the multicollinearity will resolve. Right? You can still check your residuals. Still random. You just save the residuals. You can explore again. Always the last one you created. That's the one. Okay. So the p-value is still more than 0.05. So that model is valid. Okay, which model? This is the model. Are we clear? Question? Okay, let's go to reporting. How to report this? We've done this for t-test, ANOVA, chi-square, and so on. And let's see how to report this. For most of you, PhD and masters, this will be minimum. Of course, we expect much more than that. We must have at least this. And nowadays, we have much more sophisticated methods that learn higher levels. But now you're moving into degree level. From diploma, today we're moving to degree level. Reporting results from regression. I wouldn't say, don't say it, all right? Results from regression. Let's say in the chapter 4, this is 4.3. Again, first test, tell what are you doing. Don't go straight to the results. So you must tell us what your intention was for this analysis. So your objective was, so what's your objective here? To test association or to test variables that are associated with BP. BP with all this. Right. So what method do you use? Multiple linear regression. So where are the results? So results in table X. All right. What is needed in this table? So go to your output. Do the enter method. Enter. All right. So that's the table I need. I don't need collinear tolerance. Only we have. What's the connection between these two? 1 divided by tolerance is VIF. 1 divided by 0.7 is this. So why do we need this? All right. So these are values you need. Copy, paste it. We leave like that. Value again. You must modify the table. First time I give you excuse. After this, no more. You can follow the notes. All right. What is this? This is unstandardized. This is standardized beta. Unstandardized coefficients. This is a t value. This is a p value. And that's a vi. Again, they must follow the same font size, font type, and font size. If this is times 12, this also must be times 12. Adjust the table. All this must be less than. Don't just leave it at 0. Sometimes it's better put 0 in front. But sometimes when you type and then when they're printing or whatever, sometimes won't be, the point may not be so visible. So better put zeros in front. All right. So we don't need this, take it out. Shading hand on it. Say these are predictors. On color. All right. Okay, then explain. What you see here, whatever I see here. First part. So what did you see in the table? Only these variables. Now we have a problem here. There is a problem of multicollinearity. Okay, then you write the equation. I didn't report the results from scatter diagram, correlation, all that, because these are things that go through to more or less say what is that you're looking for. Next, mention the R square. It's very important. Even it's only 33% is still reported. Don't say too small, I don't report. That is good for the next person who does the research. He or she knows that we need to take other variables besides this. And then we have predictors with his stepwise analysis. Only these variables again. R square so much. And this is okay. Finally, that's the equation. Why am I highlighting? That means you haven't lost much of the explained variation when you do the stepwise. So don't have to say 0.3, which means no need. It's already telling that only these variables were significant. Okay, so don't have BSA here. Okay, that's what goes into your item. Of course, you can add a bit more, but don't tell grandfather, grandmother story. Basically telling what you're going to do and how you did it, and the results, and what the results mean. Okay, that's all we need. Okay, listen here, I want to draw attention to this. The R square and adjusted R square. The R square and adjusted R square. Right? If these are very much different, then you report adjusted R square. Adjusted for the sample size and number of predictors. Adjusted for sample size and number of predictors. If these two are very much different, that means you're putting too many variables unnecessarily. Right? Sometimes they overinflate and report only this. In our case, both are almost same. It's okay to report either one. So once you're done with that, so we have an exercise. Okay, that's exercise. What I want now is I have a DBP, BMI, weight, and TG. BMI, weight, and TG. Oh, there's no height. Can't compute that, huh? I'm going to change this, huh? You can't compute BMI because I didn't put weight, height. Let's see. So BMI change to okay, cholesterol. Right, I want these variables. TCH, total cholesterol, TG, triglyceride. So what I want is similar to what you've done. Gita, how long will it take to do this? Gita,
Yes, bro.
how long will it take to do this?
10 minutes.
Huh?
10 minutes.
10 minutes, huh? Okay. Now the time is 4:42.
Oh, 20 minutes.
Huh?
20 minutes, bro.
10 minutes, huh?
20 minutes, 20 minutes.
Or 20 minutes. Okay, 20 minutes. Okay, 5:15.
Okay.
Do this and send me.
Okay, bro.
Professor, my computer is very slow with the school Spss system.
Okay.
Waiting for download is very long time, and then I can work. So
You did a Mac or what? Which
my
Mac?
MacBook, yes,
Mm,
because it's always have problem. Even I just so
okay. All right. All those can finish by this time. You submit.
I can, well,
Those who
I try
can't,
to submit it.
those who can't be late also can. But make sure you do it.
Yes, I